Warrior 1 and Warrior 2 are just two examples that emphasize the critical role of space probes in expanding our understanding of the universe. These extraordinary spacecraft act as our eyes and ears in space, venturing into territories far beyond our reach and providing us with real-time data about our solar system. Through their instruments and sensors, they relay information that helps scientists study cosmic phenomena from a distance, overcoming the limitations that prevent direct exploration. For many years, these probes have been essential tools in our quest to learn more about space, giving us insights we otherwise couldn't obtain. Recently, however, Voyager 1, one of NASA's most iconic space probes, has been sending back strange data from deep space, raising concerns among NASA engineers. They've begun to question whether Voyager 1 is encountering something unknown or if there's an issue with its systems. Could these signals represent an unusual message from deep space? Or is there another explanation? This mystery has prompted further investigation, leading us to explore how Voyager 1 has been influenced by mysterious forces beyond the familiar regions of space. For nearly 45 years, the Voyager missions have been at the forefront of space exploration, providing some of the first and most significant observations of our solar system. Launched in 1977, NASA's twin Voyager spacecraft, Voyager 1 and Voyager 2, were designed as exploratory missions to visit the outer planets of our solar system. These spacecraft are incredible in their longevity and performance, serving as time capsules from a different technological era. Each Voyager probe is equipped with an 8-track tape recorder, a technology that by today's standards is ancient and vastly inferior in terms of storage capacity. For comparison, the data storage on the spacecraft is billions of times smaller than that of modern smartphones. Even more astonishing is that the Voyagers transmit information at a speed that is up to 38,000 times slower than the internet connections we use today. Despite these limitations, both Voyager 1 and 2 have continued their journey through space long after completing their initial missions, and are now the only human-made objects to have ventured beyond our solar system into interstellar space. Their ongoing mission is to traverse the vast and largely uncharted regions of space, collecting data that gives scientists a unique perspective on the boundaries of our solar system and its interactions with the greater cosmos. Their journey has allowed us to observe the interactions between the solar wind and the interstellar medium, providing scientists with unprecedented data for comparison between early and more recent observations. No other spacecraft has had as significant an impact on our understanding of the Sun and its role in shaping the space environment as the Voyager missions. They've revolutionized the way we see our solar system, but their contributions go beyond just scientific data. Each Voyager spacecraft serves as an ambassador for humanity, carrying with it a golden record, an iconic artifact intended to represent the diverse culture and knowledge of Earth. These records contain music, greetings in various languages, and images that showcase life on Earth, as well as diagrams explaining fundamental scientific principles. These messages were designed with the idea that if any intelligent extraterrestrial life were to encounter the spacecraft, they would have a glimpse into who we are as a species. The gold coating on the records is specially designed to withstand the harsh environment of space, ensuring that these records could survive for over 1 billion years, remaining intact even as the Voyagers drift further away from our planet. In many ways, these records are like cosmic time capsules or messages in a bottle floating through space, with the hope of reaching another civilization. Scientists have been surprised by some of the findings sent back by the Voyagers, especially regarding the interstellar magnetic field. The data collected has sparked debates among experts, particularly about the shape and behavior of the heliosphere, which is the magnetic bubble created by the Sun that surrounds and protects our solar system from the interstellar medium. For a long time, the heliosphere was thought to be comet-shaped, with a long tail extending behind it. However, new observations suggest that it may be more spherical than previously assumed. This discovery has raised new questions about whether the heliosphere changes in response to the Sun's activity, such as the appearance and disappearance of sunspots, or if it remains relatively constant over time. As the Voyagers continue to explore beyond the heliosphere, they are providing crucial clues that help scientists piece together this complex puzzle. The boundary between the solar wind and the interstellar medium, known as the heliopause, is another area of great scientific interest. The solar wind consists of charged particles emitted by the Sun, which stream out into space, forming a protective bubble around the solar system. However, this bubble eventually gives way to the cooler, denser plasma of the interstellar medium, the space between stars. Much like how Earth's atmosphere has layers and boundaries, the solar system has its own distinct layers, with the heliopause marking the outermost edge. When Voyager was launched, scientists were unsure how far this boundary extended. They initially thought that the heliopause might be located near Jupiter, but as the spacecraft traveled farther, it became clear that the boundary was much more distant than originally anticipated. As Voyager 1 journeyed through the outer planets, it detected radio signals that were thought to be linked to solar flares, massive eruptions of energy from the sun. These signals, recorded at frequencies of 2 to 3 kilohertz, were too weak to be detected from Earth but could be picked up by Voyager as it passed through the outer edges of the heliosphere. These radio waves are believed to have been generated by electrons vibrating in response to the plasma ejected by solar flares. The plasma then interacted with the heliopause, causing the vibrations that produced the radio waves. This interaction gave scientists a way to measure the distance to the heliopause, which was determined to vary between 116 and 177 astronomical units, AU. On August 25, 2012, Voyager 1 crossed the heliopause at a distance of 125 Australian dollars, officially entering interstellar space. The data sent back confirmed that Voyager had left the heliosphere, as the spacecraft detected the disappearance of high-energy particles from the solar wind and an increase in cosmic rays from outside the solar system. However, not all scientists were immediately convinced of Voyager 1's crossing. One of the key instruments on Voyager 1, the plasma instrument, had stopped working earlier in the mission, preventing it from measuring the sudden increase in particle density that would confirm the transition from the heliosphere to interstellar space. Furthermore, the magnetic field data presented another puzzle. Scientists had expected the magnetic field outside the heliosphere to have a different direction from the one inside, but Voyager 1 found that the orientation of the magnetic fields was surprisingly similar. This unexpected result remains a mystery, with no clear explanation for why the magnetic fields inside and outside the heliosphere are aligned.
The sun played a crucial role in this discovery as well. In early 2012, solar storms began to send shock waves through space, and by the following year, these disturbances had reached the plasma that Voyager 1 was passing through. As a result, electrons in the plasma began to oscillate, generating radio waves that Voyager 1 detected. These waves provided further confirmation that the spacecraft had entered a region of much denser plasma, a key indicator that it was now in interstellar space. 6 years later, in 2018, Voyager 2 also crossed the heliopause on November 5th. This time, the spacecraft's plasma instrument was fully operational, and it recorded a significant increase in the density of charged particles, such as protons and electrons, as well as a sharp rise in temperature, ranging from 30,000 to 50,000 Kelvin. These readings were much higher than expected, likely because the plasma had been compressed as it entered the heliosphere. As with Voyager 1, Voyager 2 observed a decline in the solar wind and an increase in cosmic rays from outside the solar system. Interestingly, the magnetic field once again did not change in direction, confirming that the similar results seen with Voyager 1 were not an anomaly. This suggests that the magnetic fields in interstellar space may be more complex than previously thought. The relatively close proximity of the heliopause to both Voyagers also indicates that the heliosphere may be stronger and more resilient than earlier models predicted. Both Voyager 1 and Voyager 2 continue their journey beyond the heliosphere, moving farther into interstellar space each day. The signals they send back take more than 22 hours to reach Earth, traveling at the speed of light across the vast distance. By the end of 2023, it's expected that Voyager 2 will have traveled 29 Australian dollars, making it the second farthest spacecraft ever launched, just behind Voyager 1. These two probes are traveling in opposite directions, with Voyager 1 headed toward the constellation of Ophiuchus and Voyager 2 moving toward the constellation Sagittarius. Despite their distance, both spacecraft continue to provide valuable data, including reports that Voyager 1 detected a hum related to waves in localized regions of gas in the otherwise empty space between stars. As the plutonium fuel that powers the Voyager probes gradually degrades, it generates less heat, which poses a challenge for the spacecraft's continued operation. NASA engineers have had to make difficult decisions, turning off non-essential systems to conserve power. This includes disabling the heaters that protect some of the scientific instruments from the extreme cold of space. Despite the lack of heat, 5 devices whose heaters were turned off in 2019 are still functioning, which has astonished scientists. The fact that these instruments are still operational at temperatures much lower than anticipated is a testament to the resilience of the Voyager spacecraft and a mystery that NASA engineers are still trying to understand. In 2022, Voyager 1's attitude control and articulation system, which keeps the spacecraft's antenna pointed toward Earth, experienced a malfunction. This system is crucial for maintaining communication with Earth, and when it failed, Voyager began sending back incorrect telemetry data. This error was traced back to a computer on board that had stopped working years earlier. The malfunction confused the spacecraft and disrupted its ability to determine its orientation. Fortunately, NASA engineers were able to resolve the issue by resetting the system using an older computer, allowing the spacecraft to continue transmitting data. However, the incident raised concerns about the longevity of the mission and whether the time had come to consider retiring the Voyagers, given their advanced age and the increasing challenges they face. Despite these challenges, the Voyager mission remains viable, and many scientists are already exploring the possibility of developing successors to these groundbreaking probes. The Voyagers have exceeded all expectations, but their power source is finite. As the plutonium that powers them continues to degrade, the spacecraft will eventually be unable to generate enough heat to keep their systems running. Over time, the plutonium produces less energy each year, leading to the inevitable conclusion that the Voyagers will one day go silent. Until then, however, they will continue to send back data from the farthest reaches of space, providing humanity with a glimpse into the unknown regions beyond our solar system. The Voyager missions have not only expanded our understanding of the solar system, but have also inspired generations of scientists and enthusiasts. As these probes travel through interstellar space, they continue to serve as symbols of human curiosity and ingenuity. Their journeys have sparked interest in topics ranging from astrophysics to engineering, encouraging young minds to pursue careers in science and technology. As Voyager 1 and Voyager 2 journey farther into space, they are entering regions that have never been explored by humanity. The unique data they gather will provide insights into the conditions of interstellar space, including the temperature, density, and composition of the plasma and magnetic fields. This information is crucial for understanding the nature of cosmic radiation and its effects on both spacecraft and potential future missions to other star systems. Scientists are particularly interested in the cosmic rays detected by the Voyagers. These high-energy particles, originating from outside our solar system, can pose a significant risk to astronauts traveling beyond low Earth orbit. Understanding their behavior and how they interact with the heliosphere will be essential for planning future manned missions to Mars and beyond. As we prepare to explore more distant destinations, insights from the Voyager missions can help develop strategies to protect future explorers from harmful radiation. In addition to studying cosmic rays, the Voyager probes have the capability to measure the magnetic fields in interstellar space. The observations made by the Voyagers challenge existing models of the heliosphere and suggest that the magnetic environment is more complex than previously thought. The implications of these findings extend to our understanding of the Sun's influence on the solar system, including how solar activity can impact the Earth's climate and technological systems. Voyager 1 and 2 are equipped with various scientific instruments, including magnetometers, cosmic ray detectors, and plasma science instruments. Each instrument has been specifically designed to measure different aspects of the interstellar medium. For example, the cosmic ray detector helps scientists understand the sources and behavior of high-energy particles that bombard the spacecraft, providing valuable information about the composition of the universe. The golden records carried by the Voyager probe serve as a cultural archive of humanity. Beyond their scientific significance, these records contain a carefully curated selection of music, sounds, and images from Earth, intended to convey a message about our civilization to any extraterrestrial beings that might encounter them. This ambitious project reflects our desire to connect with the cosmos and share our existence with others, fostering a sense of unity among people from diverse backgrounds.
As the spacecraft continue their odyssey, they provide a unique opportunity to study the interactions between the solar wind and the interstellar medium in real time. The data returned by the Voyagers allows researchers to analyze the dynamic processes at play, contributing to a deeper understanding of astrophysical phenomena. This ongoing research helps refine models of stellar and galactic evolution, as well as the formation of planetary systems. The longevity of the Voyager missions has also opened discussions about the future of space exploration. As we look to the stars, scientists and engineers are contemplating new technologies that could enable us to send more advanced probes to distant exoplanets. Concepts such as solar sails, laser propulsion, and autonomous navigation systems are being explored to enhance our capabilities in deep space exploration. The knowledge gained from the Voyagers will inform the design and implementation of these future missions. Moreover, the international collaboration sparked by the Voyager missions has paved the way for cooperative efforts in space science. Countries around the world are now working together on ambitious projects aimed at exploring the outer solar system and beyond. This spirit of collaboration is crucial as humanity faces common challenges, such as climate change and the need for sustainable practices in space exploration. As the Voyager probes continue to send back their precious data, they are not merely collecting information. They are weaving a narrative about our place in the universe. The stories told through their findings reflect humanity's quest for knowledge, understanding, and connection to the cosmos. With each transmission, Voyager 1 and Voyager 2 reaffirm the idea that the exploration of space is a shared endeavor, transcending borders and cultures in the pursuit of discovery. In the coming years, as we receive further data from these remarkable spacecraft, we can anticipate new revelations that will reshape our understanding of the cosmos. The legacy of the Voyager missions will continue to inspire future generations of explorers, reminding us of the boundless possibilities that lie beyond our home planet.